Well, thank you very much for the opportunity. And I work for the, as I just noticed, the Unspecified Institute for Solid State Physics at Graz University of Technology. And I work in Oliver Hofmann's group. And as the title suggests, I'm interested, or we are interested in the structures that molecules form if they adsorb on surfaces. Molecules like tetracyanoethylene, naphthalene, or benzoquinone, or small rigid molecules in general. And to give you a sense of what structures we are considering, there are some examples of structures that we've already studied, like if we put TCNE on silver 111, we get these nice chevron structures, and naphthalene and benzoquinone on copper 111 and silver 111 respectively also form nicely regular structures, right? And we would like to predict structures like these from first principles, right? So what we're doing is we take a molecule and a substrate, and then we would like to find which configuration of the molecule on the substrate is lowest in energy. So we would like to find the adsorption energies and find preferably the global minimum. And this is in principle an infinite problem because there are infinitely many ways to arrange the molecules on the substrate. So what we need to do as a first step is we need to do some coarse graining. And even if we do that in a very smart way, we will still end up with far too many configurations of molecules on the surface to consider. So we have to do machine learning. And we use Bayesian linear regression as our machine learning model. And that then allows us to predict not only the adsorption energies, but also get some physical insight into the system we are considering. And in this presentation, all of this is encompassed within the sample approach, and this is the approach we've been working on for the last 2 years. And in this presentation, I'm going to focus on the machine learning part of sample, and I'm going to show you some of the cogs and gears of that. But before I do that, let me very briefly introduce the coarse graining part. So the core premise is commensurability. And commensurability means that the unit cell of the adsorbate layer is a supercell of the substrate. So we can define a couple of substrate supercells of different areas so that we can generate structures of different coverages. And then we add to these structures what we call local adsorption geometries. And the local adsorption geometry is the way an isolated molecule likes to snap onto the substrate. And we arranged all these local adsorption geometries in every possible way in our supercells, and that gives us a set of configurations. So how many configurations are we talking about? Well, here is a plot of the number of configurations, and on the y-axis you can see the number of molecules that we put in the unit cell. In this case, it's naphthalene on copper 111. And if we want to study the experimentally relevant coverages, we have to look at about 40 million possible configurations of molecules in our unit cells. So clearly far too many to calculate, and I should mention, we use density functional theory to calculate the adsorption energies. So we need to do machine learning, and Bayesian linear regression needs, as we've heard today already, a couple of ingredients. Namely, we need a training set, so we select a couple of these coarse-grained configurations. Then we need an energy model that should allow us to calculate the energies very efficiently, and through machine learning we would like to find the model parameters of the energy model, and we also require some prior knowledge that we want to put in. So let me start by talking about the energy model. And the energy model we are using is very simple. It consists of 1- and 2-body interactions. The 1-body interactions are the interactions of the molecule and the substrate, and the 2-body interactions are the interactions between pairs of different molecules. And if we sum them up for a particular configuration of molecules, we find the adsorption energy of that configuration. And the 1- and 2-body interactions are our model parameters, and each 1-body interaction corresponds to a particular local adsorption geometry, and each 2-body interaction to a particular pair of molecules. And if we have a configuration like this one, we can identify which 1- and 2-body interactions occur. So for instance, the first 1-body interaction we find once, then the second 1-body interaction doesn't show up in this configuration. The first 2-body interaction actually shows up 4 times here, but we account for it twice because this one up here already accounts for this one, so we avoid that double counting. The second 2-body interaction doesn't show up in this configuration. The third one we account for once, the fourth one twice, and this should also demonstrate that we are not only looking at next nearest neighbor interactions, and the final 2-body interactions don't show up in this configuration. And by adding up the 1- and 2-body interactions according to these numbers, we get the adsorption energy of that configuration. And because we have done some coarse graining, and that because if the molecules are at a large distance, we can assume that the 2-body interactions go to 0. We can describe all our millions of configurations with just about 1,000 1- and 2-body interactions. So there are 1,000 parameters that our machine learning model needs to learn, and For that, we require some prior knowledge. The prior knowledge we can split up, or for the sake of this presentation, I've split up into prior covariance, which is concerned with the correlation between the different one and two body interactions, and the prior mean being the value we assign them without having done calculations. So let's start with the prior covariance, which, as I said, is concerned with finding a covariance matrix for the one and two body interactions. And since we only have about 10 one-body interactions, we can say that if they're the same, we say that they're correlated with one, and if they're dissimilar, we say that they're uncorrelated. One and two body interactions are obviously something different, so we can say that they're uncorrelated, and similar two body interactions obviously are also correlated with one. It gets a little bit more interesting if we look at different two body interactions where we would actually like to calculate a correlation, and to do that we use this equation, which has the form of a Laplacian kernel. And the main ingredient is this difference between two descriptors, and theta down here is just a parameter. And the descriptor is just a translation of a pair of molecules, in this case benzoquinone molecules, into a vector of numbers that we can plug into this equation. And the particular descriptor we've come up with is based on distances between different atoms on the two molecules. And each element has 1 over the distance to the power of a parameter n. Why 1 over the distance? Because if we have small distances are going to be more important for the interaction energy of these two molecules than large distances. Small distances will give us large elements in our descriptor. Large distances will give us small elements. Also, if we change a small distance, it will have a larger change in the element of our descriptor. But this is still not descriptive enough, because we have different species, right? So we have oxygens, hydrogens. So we split the feature vector into different sections belonging to distances between hydrogen atoms, distances between hydrogen and oxygen atoms. And again, we do the same thing. We have the same structure of the descriptor, just for different pairs of atom species. And with this descriptor, we can now calculate our correlation. And with this, we come to the energy values that we assign our one and two body interactions before we have done calculations of densely packed configurations. And we have a pretty good idea about the one-body interactions, because we can put an isolated molecule on the surface and calculate it. And the one-body interaction will be relatively similar to that interaction of an isolated molecule with a surface. And we allow for the one-body interaction to vary from that by defining a Gaussian. We do the same thing for the two-body interactions, but here we don't know whether they're going to be attractive or repulsive, so we start with a non-interactive prior. We say that the value is 0 in the beginning, and we use a broad Gaussian, as you can see here, if the molecules are close to each other, because then they can become very attractive or very repulsive, and a narrow Gaussian if the molecules are far apart from each other, because then we push the two-body interactions closer to 0. And that accounts also for the decay of the interaction with distance. And with all of that, we can now think about which configurations we actually need to calculate. And the easiest way, I guess, to pick them would be at random. And here you can see a training curve. And for TCR neon copper 111, this did really badly, as you can see. Second random run didn't do much better. Third random run, fourth random run. Fifth random run, now it did better, and it had made this big jump down here. And this indicates that there is a configuration that it really needed to learn. And we would like to find these configurations systematically. So we would like to find a much better training set than just picking it at random. So what we can do is we can think back to our one and two body interactions. And if we have a configuration, as I said, we get different one and two body interactions in this configuration. And let's just pick a very naive training set. Let's just calculate this one again. And that gives us the same numbers. And we can see this as a matrix. We call this matrix X1. And this will represent our training set 1. Let's think of a different training set. Keep the first configuration. Let's take another one, a different one. This time it gives us a new set of one and two body interactions. And we call that matrix X2. And we would now like to evaluate which of these training sets is better. Now, question for the audience, which one is better? I guess you would agree with me that it's the second one, but how do we do this systematically, and if we have larger training sets than just two? So what we can do is calculate the posterior covariance matrix, which has, in our case, as its inputs, a part where the interactions in the training sets factor in. So here we would have for training set 2, x2, t, x2. Sigma is a parameter, and the inverse prior covariance matrix, the one I've talked about before. And now there are a couple of ways to evaluate that come from experimental design theory. A couple of optimality criteria. The particular criterion we've chosen is called the optimal selection, and it seeks to maximize the determinant of the inverse posterior covariance matrix. And what this does is the first term leads to us preferring a training set with interactions that are as diverse as possible, and the second part with a prior covariance matrix leads us to prefer interactions that are as uncorrelated as possible, right? So we have a training set with many different interactions that are uncorrelated, and that should maximize what we learn. And indeed, if we do that if we evaluate the d-optimal selection criterion for our training sets, the second one is much better. And the impact becomes even more obvious if we look now at our example of T-senior and copper 111, where we get a significantly better training curve than the random samples. Right, and with this, we can now come to the part where we calculate the parameters of our energy model and actually gain some physical insight from our calculations. Because you remember, we only calculated adsorption energies of densely packed configurations, right? But we can now take a look at our model parameters, and this is a qualitative insight. But still, if we put two naphthalene molecules on the surface and move one around and draw the two-body interaction, we find that they are always repelling each other, and that's because they get positively charged on the surface. It gets more interesting if we look at benzoquinone on silver 111, for instance, where we have areas where they're attracted to each other and areas where they're repulsive. And that's because the oxygens and the hydrogens have attractive interactions. Right? And we can find out things like these, and they can help us explain why a particular configuration of molecules is more energetically favorable than another one. And if we take all of these interactions together, we find the total adsorption energy. Right? And this one I show you here for naphthalene on copper 111, ranked from 1 to 40 million. On the y-axis, you can see the energy per unit area. And we've picked a training set of about 260 configurations and predicted all the 40 million configurations. To find how well we did in our prediction, we picked another 64 test points, this time at random, and we made sure that they were not part of the training set. We calculated them also with density functional theory and compared the calculated and the predicted adsorption energies. And this allowed us to find a root mean square and a maximum error of 0.03 electron volts per nanometer squared. And if we compare that to the numerical conversion settings to which we chose for our DFT calculations, which were 0.05 electron volts per nanometer squared, we find that indeed we are capable of predicting adsorption energies of densely packed layers of molecules on surfaces to within the numerical uncertainty of our DFT calculations. And on that very positive note, I would like to summarize. So we started out with a basically infinite problem, and we whittled that down with coarse graining to something finite, and then we picked a couple of these configurations, trained as a training set, trained our Bayesian linear regression model, which before we did that, supplied with an energy model and some prior knowledge, and then we found the model parameters, and those parameters then allowed us to gather some physical insight into our system and also to predict the adsorption energies of millions of configurations. And with that, I would like to thank my colleagues, my boss, Oliver Hofmann, and of course, I would like to thank you for your attention.
Actually, could you tell us a bit more about the Bayesian method that you used? I mean, you said that you,
Bayesian linear regression.
Bayesian linear regression. That means that you have an energy model. It's
we have an energy model, and basically I could if I could do a linear regression on the energy model, yes, I could just solve that. But first of all, there are too many parameters. Doing 1,000 calculations is already pretty difficult, and it's difficult to find configurations that give us a vector of 1- and 2-body interactions which is linearly independent, right? So we use what we could say, or what we could see as a regularization. Also, we use a covariance matrix, yes, okay, that defines some similarity between our 1- and 2-body interactions.
Okay, and when you showed the graph with the colors that showing positive and negative attraction,
yes,
essentially all of those points are at different basically a different interaction
These
that
are
is modeled,
different parameters in our
different
energy model.
parameters that you learn. Okay.
So this is actually, you can actually see what we are learning here.
Okay. Yes.
I have a question
Yeah.
about the similarity measure you use. Is there any advantages on using the Laplacian instead of a Gaussian? Did you think about the implications of that on the
Actually,
system?
we tried out a couple of different norms. As you can see, we had the L1 norm in there, and they didn't really perform differently. So we just stuck with that. This was the first one we've implemented and tried out a couple ones.
Thank you. Yeah, I was wondering about the importance of the surface essentially for your ideal set.
Yes.
So you have a copper 111. So if you think of a copper 001, for example, so would you then have an ideal learning curve for the same set of structures, or do you expect different structures?
We will get certainly a different set of configurations, but we actually use that for silver 100, so it's the same symmetry, I think. So we would get the same performance of our model.
Thank you for the talk. I was wondering, when you generate the training data,
Yeah.
do you fix the molecules epitaxially at specific positions without relaxing them? Because my belief is that in a real simulation, if you put two molecules together, they might not be any more situated at the perfect HCP or top position.
That's an excellent point. So this assumption of commensurability, that carries the implicit assumption that we say that the potential energy surface of a single molecule on the surface, the potential well it sits in, is deep enough so that it doesn't get pushed out from that by molecule-molecule interactions. So we assume that the molecules, if we put them in a densely packed layer, remain in the same position, or in the relatively same position. We have tried this out for the system of naphthalene. We did some calculations where we optimized the geometry by doing gradient descent, and there we didn't see significant changes in the geometry, except for if we put the molecules far too close together, but then the energies were so high that they wouldn't show up in experiment anyway, or in our then we wouldn't predict these as low energy configurations anyway.
Okay, we have time for a last question.
Can you extend that? So once you've got your interaction potentials, can you extend the model to disordered layers? So not just commensurate versions?
So the machine learning model, certainly. The part where we build configurations is difficult. First of all, by calculating our training data with density functional theory, we are limited to periodic boundary conditions. So disorder is already difficult there. Building disordered configurations, we would certainly have to look at something different. Right now, we're just doing the combinatorial route, trying out every way the molecules can sit. But the machine learning part would certainly be able to handle that.
Okay, let's thank Lukas once again.